All right, so let's do a little recap of where we are in the class so far. We started with the simplest model of linear regression. We had a linear hypothesis space and square loss, and we used that as a vehicle to talk about some optimization, gradient descent, and stochastic gradient descent. And the next week last week we introduced regularization, L1 and L2 regularization, and we spent a lot of time developing tools to do the optimization when we add this regularization into our objective function. And we also spent a lot of time thinking about kind of the implications of L1 and L2 regularization and their properties. And so far that's the linear hypothesis space and square loss, and then we added in the L1 and L2 regularization. So this week we're going to kind of open up that loss function, and we're going to talk about different loss functions we can use besides square loss. And then we're going to focus in on one particular loss function called the hinge loss. It's the loss function for support vector machine. And we're going to go a little bit deeper in the properties of what results when you use the hinge loss. And that'll give us opportunity to go through some Lagrangian duality theory, which has some other benefits later in the course. OK, so loss functions for classification and regression. So let's first talk about regression loss functions. So far, we've only spoken about regression. So let's dig into that a bit. So in regression, we have our input space is RD. What we're producing, our action, is a real number. Our outcome space that we're trying to match is real. So the more common notation for a regression setting is what we're predicting we'll write as y hat. And what we're trying to predict, that's y. Y hat and y. All right. So in that case, a general loss function for regression would take a y hat and a y as input and produce some real number, the loss on y hat and y, as output. So that would be kind of the generic form of a regression loss function. But usually, regression losses only depend on what's called the residual, which is the difference between what you wanted to predict and what you actually predicted. Right? It's what you would have to add to your prediction to get the exact right answer. That's the residual. And there's a term which is distance-based. They say a loss is distance-based if it only depends on the residual. So if we could rewrite this general loss function that takes y hat and y as some other function of the difference, some function of the residual. Right? And moreover, we want the loss to be 0 when the residual is 0. Right? So if we nailed it, 0 loss. So that's distance-based loss function, just a little terminology. So one thing about distance-based loss functions is they are translation invariant. So what that means is that if the correct answer is 10 and I predict 9, what's my residual? 1, right. And it's translation invariant in the sense that if the correct answer is 100 and I predict 99, the residual is the same, so my loss is the same. I'm off by 1, so the loss is the same. So wherever we shift the correct prediction to, say if we shift by A, the loss is the same. But here's the question. When might you not want to do translation invariant losses? So the issue would be like percent error, right? So if you predict 9 and the correct answer is 10 versus predicting 99 and the correct answer is 100, a lot of cases 99 out of 100 is a lot closer than 9 out of 10, right? Because it's like relative error. All right, so we don't always want these translation invariant losses, but you can often transform your y's to a scenario where translation invariant is fine again. All right, so let's talk about some concrete losses for regression. We, of course, have the square loss. I've now written in terms of R, the residual, which is just the difference between actual and what we predicted. But there's another loss, the absolute loss, or Laplacian loss, which has some nice properties. And so to get there, we'll look at some actual losses. So here's a little table. In the first column is y, the true value of y. And we'll assume in the second column that y hat is always 0. And we want to look at what are the losses we get when we predict 0 for varying values, true values of y. And in the third column, we have the Laplacian, or absolute loss. And in the fourth, we have the square loss. And the point of this table is to show that the square loss penalizes really heavily for big errors compared to the absolute loss. So if you have a particular data point that for some reason or another has a large residual, the square loss is going to really focus your objective function on that one point, because the penalty incurred is huge compared to the others. If the typical loss on your training data is maybe between 5 and 10, most of your losses are between 25 and 100. So when you look at your average loss, you want it to be about 25 or 100, but that one point that has a residual of 50 has a loss of 2,500. That's going to really dominate your objective function. But if you use this absolute loss, it's more controlled. So no single point can overpower your objective function. So the consequences are we get some robustness. So here's the data set. Each of these black circles is a data point, and we're fitting it with linear regression. But in one case, we're using square loss, and that would be this red fit. And in the other case, we fit with the L1 loss. That would be this blue fit. And what we're seeing is that these three outliers down here really pull the fit down. So the fit doesn't really go through any of these points. These are the points up here are probably it's probably what you want to fit. You probably want the line that goes through these points. Whereas the outliers really pull you down to no man's land. It's not really capturing the outliers or the inliers, you might say. Whereas the Laplace is much less affected by these outlying points. All right? And that's just a simple consequence of the idea in this table, that the loss from the outliers is really huge, dominates your objective function. So in square loss, you're doing all you can to minimize the objective function. A lot of that is trying to fit these points as well as you can. All right? OK. And there's other loss functions, too, for regression, although these are the two most common. And there's one extra that's worth knowing about. It's called a Huber loss. And that's it's kind of between the L1 and L2. And the reason that we introduced that is because the L1, while robust, is not differentiable. So it's a little bit more of a challenge to work with, right? Last week, we had a lot of discussion about how to handle lasso, exactly because it wasn't differentiable. We had this absolute value in there. So there's this other loss called a Huber loss, which kind of interpolates between the L1 and the L2. So close to 0, so for rather little loss, it's like square loss. And further away, it's more like L1 loss. It's more linear. And what's nice is that you can do it smoothly so that it's differentiable everywhere. So it's got the robustness properties. And the sorry, let me explain this graph. I jumped into this too quickly. So what this graph is, on the x-axis is the residual, right? Because this is a distance-based loss. The loss only depends on the residual. So the residual of 0 means no error. So here, the y value gives you the loss of each of these three loss functions in terms of the residual. So at 0, the loss is 0. And as we get further away from 0, so way out here, we have kind of really bad residuals, maybe from an outlier or something. And this L2 loss will be really large. That's what makes it not very robust outliers. Whereas this L1 and Huber loss, they just increase linearly. And so it's not that it'll completely ignore outliers, but the effect of the outliers will be much less than if we use this square loss. Is that clear? OK. All right. So that's probably enough to say about regression loss functions. Those three will get you pretty far. So let's move on to classification loss. This will be the first time we really talk about classification. And we're going to need a different type of loss function for that. So in the classification setting, we have this outcome space -1, 1. We're going to write our labels as +1 and -1. And the action space will start with 1 and -1. And then the most natural loss is the 0, 1 loss, which we mentioned in the first lecture, which is simply if our prediction is equal to what we want it to be, we have no loss. And if it's wrong, then we have a loss of 1. That's the 0, 1 loss. And it turns out if we use this, if we try to use this, we'll find that we can't optimize our objective function. You could plug this into empirical risk. You can plug in that loss function. but I have a slide in a few that claims that that's not a tractable optimization problem. So we're going to relax the setting a little bit. And rather than having an action space that's 1 and -1 actually producing classifications, we're going to allow predicting real values, just like in regression. But we'll take it as a convention that if the value we predict is positive, that's going to be mapped to predicting 1. And if it's negative, that'll be mapped to predicting -1. All right? But now we can have hypothesis spaces of functions that produce real values instead of 1s and -1s. And it'll allow different loss functions that are more tractable and easier to work with. So now we've changed our action space from 1 and -1 to reals, because we're producing reals. And we'll have a real value prediction function. So I just wanted to pause here and say, this is kind of the first time that we have some justification for separating out the action space and the outcome space. Because now we really want to produce something that's different from the label in our training data. We're not really producing 1s and -1s. We're producing numbers with this relaxation. So this is kind of the first reason that we have a different symbol for action and output space. So some terms. The value f of x, this is our prediction function, our real valued prediction function for classification, is called the score for input x. And f can be called the score function. And intuitively, what we want is that, so the sign of the score is the class that we're predicting. But the size of the score, we would like the size of the score to kind of represent like a confidence. So if the score is really large, then that's like maybe like 100, that would be a much more confident positive class prediction than a score of 1. Right? -5 would be a more confident negative prediction than -0.1. All right, so the next important term we're introducing is called the margin. So far we have the score. That's the number we actually produce. The margin is interesting. The margin takes the predicted score, say y hat, and the true class label, which is the number 1 and -1, and multiplies them together. So what's the effect of that? When is the margin positive and when is the margin negative? That's the question we're getting at. Yeah?
So the margin is positive when we did a good job of predicting, and it's negative when we incorrectly.
Right, so the margin is positive. So the product of two things will be positive if both of those things are either both positive or both negative. Right? And if the sign of y hat and the sign of y are the same, that means we got the class right when we actually map to our score to ±1. So we want the margin to be positive. Positive margin means we got the answer correct. Negative margin, we got it wrong, because the actual label and the predicted label are different. Yeah. What about the size of the margin? Would we want the size of the margin to be large or small? Do we want margin to be, we know we want it to be positive. Do you want it to be large and positive?
Yeah.
Because, why is that?
Because if you're multiplying.
Because?
It'll show we have higher confidence in it.
Yeah, so we want large and positive because we not only want to be right, we like to be right with confidence. Why not? All else equal. Okay. So for all the objective functions we talk about today, we're looking to, in some sense, maximize the margin. We want large margin. So you'll hear the term maximum margin a lot. And in our setting, this is what we're talking about. So just as we had a term for residual-based losses, distance-based losses, here we have the fact that most classification losses are functions of the margin. And such functions are called margin-based losses. Now, there's a related concept called the geometric margin, which it's not exactly the same, but they are related, and that will come to if we do hard margin SVM. You'll see a related concept called geometric margin. Yeah?
Why is the Huber loss differentiable? Like, how is it? Because at the point y equal to x equal to delta, b can be discovered.
Say it again. So the question is, why is Huber loss differentiable? Well, I claimed it was differentiable, but I didn't even give you the functional form of it. So you can't see it. So do you have a specific concern of why it might not be?
Because at the point x equal to delta,
X equal to delta, yeah.
there might be a discontinuity.
Yeah, so you match the derivatives at x equals delta so that it's differentiable from the left and the right. So yeah, it's constructed specifically to have matching derivatives from left and right there. Yeah. Okay. All right. So geometric margin related, but not the same. Don't be confused. The margin we're talking about today, I'll just either say margin or functional margin is sometimes the term. So here we've boldly taken the 0-1 loss and plugged it into our kind of one main formula for machine learning, which is empirical risk minimization. So this average 0-1 loss. And the issue is that this is not easy to optimize. It's not convex. It's not differentiable. It's not even continuous. And from a theoretical perspective, you can show things like optimizing this as NP hard, so not computationally tractable. So we need something else. This isn't going to do the trick. Sidebar, though, this could still be what you're interested in doing well on when you deploy. And if that's the case, when you actually evaluate proposed prediction functions, if you care about 0-1 loss, you should evaluate the performance in terms of 0-1 loss. Okay? So we're not completely throwing out 0-1 loss. We're simply saying that when it comes to finding your prediction function, when we try to optimize some objective function, we don't really know how to optimize this objective function with this loss. So we're going to have to do something else for computational reasons. But you still, if your goal is to maximize the number of correct classifications, when you evaluate the performance, you should be looking at the 0-1 loss. We just don't know how to use this to find the prediction function because we don't know how to minimize this objective function. Yeah?
So then we go to the margin-based loss to do calculations, for example.
Yeah, so we're going to replace this 0-1 loss with another loss, which will, yes, be a margin-based loss.
Then we still need a connection between these and the margin-based, right? Is there a connection saying that the parameter-based space we search, satisfy that optimization problem, actually satisfy this one as well?
Yeah, so the question is, I think the question is, is there any theoretical basis for the step we're about to take, which is where we're replacing the 0-1 loss with some other surrogate loss that has better computational properties, and you're asking, that's cute, but is there any justification that what you end up with actually works in terms of the 0-1 loss? And there is a very nice piece of theory on that. It's the thing to look for is this notion of a classification calibrated loss function, and it will turn out that the losses we talk about are classification calibrated. And so in some sense, optimizing these surrogate losses will lead to things that perform well in terms of 0-1 loss. Yeah. So the 0-1 loss. This is another this is a way to kind of graph a loss function. And let me again talk through the axes here. So the x-axis this time is the margin, right? So the margin, remember, we'll write as m. And that's going to be y, which is the correct label. And in this case, instead of y hat, we're writing f of x to emphasize the fact that this is a prediction based on an input x. So y f of x is the margin. And of course, so which side of 0 is the good side? To the right. A positive margin means correct classification, because our prediction score has the same sign as the actual class. And to the left is bad, right? And so we see that the loss on the bad side is uniformly 1, and then the loss is 0 when we're above 0. All right, let's look at our first interesting margin-based loss. It's called the hinge loss. First, let's look at the expression. Max of 1 minus m, 0. So the hinge loss is a function of m. Let's look at the graph. Has it coming down like a linear function. So we're penalizing more and more as our margin is more and more negative, so more and more wrong. The penalty increases linearly with the margin being in the bad direction. And even at 0, we have a loss of 1. And even in this region between 0 and 1, which is on the positive side of the margin, we're still penalizing. And then it finally hits 0 at the margin of 1. And it's constant at 0 to the right. So what are the properties of this function mathematically? I mean, it's continuous. That's good. convex. That's nice. It's not differentiable. That's a little annoying. It's not differentiable at 1. And a lot of the work we're going to do is how to deal with this non-differentiability. It's an upper bound on the loss function, which suggests at least if we minimize the hinge loss to a small level, that will certainly minimize the 0-1 loss, because the hinge loss is an upper bound on the 0-1 loss. Okay, that's a weak justification. It's not the full justification for using it. So we have a new term, which is a margin error. So we say we have a margin error if we're still getting some loss. We say we have a margin error if we're getting any loss from this margin loss function. But we can have a margin error even if we don't have an actual prediction error. And that's the distinction I wanted to make. So between 0 and 1, we're getting some loss, but the prediction is still correct. OK. So that's the hinge loss. And this is at the core of an SVM. So we now have all the tools to define what the soft margin support vector machine is. And we'll just do it now. Soft margin support vector machine. Our hypothesis space is a space of linear prediction functions on some input domain, RD. The loss function is this hinge loss, the mathematical expression of which is here. And we can look at that more carefully in a second. So we have the average. In this case, it's cumulative, but we usually would write an average hinge loss plus the L2 regularization term. So support vector machine is linear predictions, linear hypothesis space. It's regularized empirical risk minimization with the hinge loss and L2 regularization penalty. That's the definition of the support vector machine objective function. So you could do now SVM if you could plug this into an optimization algorithm. And we'll work through some details later on. Yeah?
Next question, is SVM itself the optimization algorithm, or what does SVM or support vector?
SVM, so the question is SVM the optimization algorithm? No, support vector machine does not include the optimization algorithm. Support vector machine is essentially this. This is the support vector machine.
So the problem definition itself is termed support.
Right. There's many different algorithms to solve this objective function. And they're all support vector machines.
A lot of times I see in paper, and sometimes in papers I see they use SVM as if it's an algorithm. They use the terminology as if it was an algorithm. So
they use the terminology as though
use SVM to solve this problem.
Right. So what does it mean to say use SVM to solve this problem? It means that you're finding a prediction function from your hypothesis space that minimizes this objective function. So more abstractly, they're probably trying to solve some classification problem. And they're going to solve it by finding a solution to this. The actual details of how they minimize this objective function, they can use any approach they like. Yeah. All right. So let's talk about this terminology. So this is exactly the positive part that we talked about last week, except now, for different conventions, the positive sign is lower instead of upper. But this is still, this expression is 1 minus m if 1 minus m is greater than or equal to 0, and it's 0 otherwise. So that's why if m is less than or equal to 0, if m is less than or equal to 0, then 1 minus m is greater than or equal to 0. And in that case, the function is just 1 minus m. So that's 1 minus m until 1 minus m is negative, and then it's just 0. All right? So you can either write it as positive part of 1 minus m or the maximum of 1 minus m and 0. And you can see that's the same thing. Any questions on hinge loss? Yeah?
So what was the reason of choosing the slope like that, like the particular slope?
So no particular slope. The particular slope actually turns out not to matter. You can change the slope. This is a convenient slope to use, basically. I think the key features that we'll want to talk about is the fact that it becomes identically 0 at a certain point and to the right, and that yields some interesting properties in the prediction functions that you get, and we'll talk about that later. And then compared to some other loss functions, let's come in a few slides to more details on that. So, yeah.
Can you please explain the formula for the loss function, the one.
Can I explain this to you?
No, the last line.
This, can I explain this to you?
Yeah.
Sure. So from our usual notation, I left off a 1 over n here. And with that notation, it would be, this is, okay. So first of all, yi fw xi. What is that? Let's break that down. So yi is the correct label for a particular example. F of fw xi is the prediction for the input xi. What kind of number is fw? What kind of value is fw xi? It's a number. It has a name. Do a little terminology review. What do we call that? It's a predictive value, but we had a score. We call it the score, right? So fw xi is the score for xi. And remember, if the score is positive, that's like a plus label. If it's negative, it's like a negative label. Now we're multiplying that by the actual label yi, which is yi is 1 or negative 1, right? So when we multiply yi by the score, we have a term for that too. It's the margin, right? So we have the score function. Now why did I put a little subscript of w on the f?
The parameters.
Yeah, so the score function is from our hypothesis space. And the hypothesis space consists of prediction functions that are linear and then parameterized by a parameter vector w. So when we're optimizing this objective function, we're searching over all w's, which corresponds to searching over all linear prediction functions. So f sub w says the linear prediction function for the parameter vector w. OK. All right, so we have yi fw xi. That's the margin. And then do we want the margin to be positive, negative, large, or small? We want it big and positive. Big and positive. So this piece is m. So now we're into the loss function piece. All that stuff we've spoken out so far is m. And then this 1 minus m and positive part, that's the loss function. And now we could go back to this picture. So when the margin yi fw xi is large, then that full expression, 1 minus m positive part, is 0. And then otherwise it decreases linearly. So have I pasted the pieces together for you enough now? OK. And then, of course, at the end, we add this regularization. OK. All right, great. That was good to dissect. Yeah?
Can you go back to where the graph is?
Sure.
Isn't it ever going to be a problem, the fact that between 0 and 1, even if our prediction is correct?
Yeah, so the concern is, why are you penalizing our prediction function even when it's correct? Because it's correct right here. It's mean. That's why would we do such a thing? And it's compromise, because there's no way. I mean, you kind of have no choice if you want something that's continuous even. Because if you want to penalize for being wrong and not penalize for being correct, all you're left with is something like the 0-1 loss. And this is very difficult to optimize. So in some sense, we don't have a choice other than to have some penalty even when we're correct. But we're going to justify it. What we're going to say is that, you know what, we actually want it this way.
Yeah, doesn't it mean that the confidence over there is very low? That's why you are penalized?
That's how we're going to argue it. We're going to say that actually, we don't even just want to be right. We want to be right with some confidence. So we're not even happy if you're just here because, you're right, but you're unsure about it. We want you to be confident. So we want to keep pushing you until you're all the way past the margin. Yeah?
So if you instead at 0, 1, you just make a right, flat line at, loss equal 1. That,
So
serve the purpose.
OK. So proposal. You're basically proposing a new loss function. You're saying, why not, if I understood you correctly, here's our 0-1 loss. That's 0-1. And then the hinge loss is like and you're saying, well, OK, why didn't you just do this loss? Oh, that was your suggestion?
The left side is still that on one analyze.
Okay.
The right side, the question is if m is very large, do we want to make it 0 or we want to make it a constant?
Oh. A constant?
Means constant 1.
If m is large and positive?
Yes.
But why would we want to? But if m is large and positive, then the prediction is correct. Why would we want to have a loss function? Why would we want to have a non-zero loss? Or why would it be constant? Do you want to draw a loss function that you suggest?
Just this one.
So,
So like this? All right.
So to make it the last equals to 0 is important, or is the function to the
Okay.
to m?
I get it. So the question is, can we shift the hinge loss up by 1? Or not even. If this is the shape of the hinge loss, are we okay? Okay. So this is a shifted version of another loss that does have a name. There's a loss function like this. Whoops, no. It's not on. There's a loss function like this. You see what I've drawn here? So this is 0. This is parallel to your loss function, right? It's a shifted back down to. So what you drew is not a shifted version of the hinge loss. It's a shifted version of another loss, the one that is linear but intersects 0 at 0 and not at 1. This new one I drew is called perceptron loss. It's sort of perceptrons. So perceptron could be written as empirical risk minimization over this loss, which is 0 at 0. Okay, but anyway, and now you're suggesting, so we've shifted that perceptron loss up by 1. Does that still work?
I think the question is all these loss functions will try to make sure that when m is large, or the loss is 0. That's the critical part of it, right? Is that really the critical part, or is it's not a function of something? As long as the constant should be fine. It doesn't really require to be 0.
Yeah, I see. So we can look directly at the objective function, and so yeah, of course, if you take this entire expression and add a constant to it, that's independent of w, and so I completely agree with you that.
Which means when I search for the minimize, I will still get the same.
You'll get the exact same answer. So it's really just a convention to have your loss function 0 when there's no loss. But yes, you're right. You could shift the loss function. I don't see any consequences of that at all.
So does the loss function work only for the 0-1 classification, or that works for like multi-class?
This does not work for multi-class yet. We'll come to multi-class in a few weeks. Yeah. Yes?
So in terms of like the step function.
Yeah, the 0-1 loss.
Other like continuous functions that can look like that. For example, like the negative of a hyperbolic tangent.
Yeah.
Why choose something that penalizes like m as it gets very negative?
Okay. So first of all, these are great questions because you do want to think about designing your loss function to be appropriate to what you think is important. So these are good questions. So the question specifically here was, why do we want to keep penalizing more and more as the margin gets more and more negative when we could have some other smooth and convenient to use function that more closely approximates the 0-1 loss? Right. So smoothness is one thing that we're looking for. There's one other property that this hinge loss has that the loss you suggest doesn't have, which is, anyone? Convexity, yeah. So the issue is that if it has that S shape, which is kind of what you're suggesting, like sigmoid, then the objective function won't be convex. And so that makes things more challenging.
But it would be differentiable.
It will be differentiable, so you can use your gradient descent methods. Whether you find the minimum or not, you will never know because it's not convex. But these days, people aren't very scared of things that are not convex as demonstrated by neural networks, which are not convex. And so folks have started experimenting with these like S-shaped curves, or even what I had drawn first, what I thought the suggestion was, is this, it's like this SVM hinge loss, except instead of continuing up linearly, it levels off to 1 when you get to 0, kind of more like the 0, 1 loss. And that's called the ramp loss. It's not convex, but you can still use your gradient methods to attempt to minimize it. So now I've drawn one more loss function. It's the logistic loss function, or a log loss. And this is exactly the loss function that you need to use if you wanted to put logistic regression, which you might have heard of in statistics, into our empirical risk minimization framework. So the shape of this curve is very much like what you're looking for. It never goes to 0. Right? It increases. It looks very linear as we go further and further into the negative direction. If you zoom out quite a bit, the logistic loss and the SVM loss look almost identical. All right? So what we'll find is that the hinge loss gives us certain properties, certain interesting properties, because it is exactly 0 to the right of some point. On the other hand, logistic loss, as you were wondering why we wouldn't have this, it's never quite satisfied with any amount of, you always want larger margin. You could always be more confident. And so it will keep pushing you to be more and more confident. So if you want to use regularized logistic regression, which is kind of, if regularized ridge regression was kind of your go-to #1 method for regression, I'd say regularized logistic regression is probably the go-to method for classification, or support vector machine if you're of that frame of mind. They're almost equivalent for the actual predictions that you produce. All right. So what about using square loss for classification? Is that crazy? So what if we literally just plugged in square loss, and y is still -1 or 1? And it turns out we can even write, so this type of loss function formulation makes sense for classification. F of x is our score function. It's real valued. Y is -1 or 1. Those are all numbers. You can do square difference. And it turns out you could rewrite this as a margin loss. A square loss is a margin loss. Turns out to be quantity of 1 minus m squared. And you could check that yourself later. So square loss is a margin loss. Let's see what it looks like. So this is what square loss looks like as a function of the margin. It's 0 at m is 1. And then it shoots up to the right. Turns out people have done some theory and experiments on this. And it's actually not that bad. So there's not really a strong consensus that this is very much worse than hinge or logistic. If you wanted to see more, I have a link to a paper on this subject. I mean, roughly speaking, they do conclude that it's not as good. They say it has a higher sample complexity than hinge and logistic loss. So sample complexity means how much training data do you need to reach the same level of generalization performance. It's a little worse. You can use your favorite regression. You can use your favorite regression algorithm to solve classification. Okay, yeah.
I don't know if you pointed out this paper or if I stumbled into it, but there was a paper which basically says as long as you have tons and tons of data, even the simplest and silliest models would work. So is it kind of that notion that if we have a large amount of data, it doesn't matter if we have some very fancy algorithm or fancy loss function, even a really simple or maybe something that looks bad to the naked eye can still do a great job.
Okay, interesting. So the vague claim is that as long as you have enough data, a very simple model can still do well. Well, I don't know, yes and no. So the complexity of the model usually refers to the hypothesis space, the types of functions you can produce. And if your hypothesis space just doesn't have a function in it that you need to fit your model, then you won't succeed no matter how much data you have. But the people who say that usually have in mind the scenario where your hypothesis space can keep growing by adding more features. So they have in mind of situations where they'll put in like millions or hundreds of millions of features of your input X, and eventually just a linear model on this huge set of features is sufficient. And you need a ton of data because when you have so many features, you need a lot of data to fit it well. I think that's usually what they have in mind, that with a lot of data. The simple models meaning linear models and with potentially lots of features. But if you just have a truly simple hypothesis space, which is to say, a fixed number of features, only linear prediction, and if the function you're trying to predict doesn't fall in the hypothesis space, you're out of luck.
That's presumably only going to be true of classification. Because for a regression problem, if your function is inherently nonlinear, I would imagine no matter how many features, unless you start adding nonlinear features, you're going to...
Right, so the point is that for an actual regression problem, if your regression function, the Bayes optimal prediction function, is highly nonlinear in terms of all the features you could ever put in there, then you're out of luck because you're not going to be able to approximate it better than linear. Right, yeah.